Hello everyone and welcome back to the session. Very good evening. So we were discussing few questions based on the basics of deep learning algorithms, the basic algorithm related to deep learning, right? What are the concepts behind that? What are the things like error functions, gradient descent algorithms? What are the types of different deep learning algorithms? Like what are supervised and what are unsupervised algorithms related to deep learning. So some set of questions were covered in the last 2 sessions or 3 sessions, right? So let's continue the same for the day. So to begin with, we have to, we all know that artificial neural network, right? ANN, and what is a perceptron algorithm? So when we talk about artificial neural networks, it is of two categories. Feed forward neural network, and it could be recursive neural network. Or you can say recursive neural network. So these are flexible to many possible variations, right? Depending upon the learning rule or inference rule or the architecture. So when you talk about neural networks, basically you will have, the basic thing is that you have the inputs, you are passing it through your integration function, then you have the activation function, and there goes the output, right? So when you talk about the number of inputs, n inputs, right, all are connected to an integration function, and whatever the threshold point is reached, then it gets activated and you get the output. So the perceptron algorithm, what we know, it's nothing but it is a fundamental unit, right? It's a fundamental computational unit, I can say, right? So it is a supervised learning algorithm and it is used for binary classification, right? Now everything is fine, good. If at all I draw, this becomes my perceptron. Now, if I make it into a normal neural network, multi-layer, right? I have the structure like this. Each input is connected to hidden layers, right? This number of hidden layers, number of neurons in the hidden layers, what should be the learning rate, all these are your hyperparameters, right? This is a network and you have connections like this, okay? So these are my input 1, input 2, input. These are my hidden layers. Maybe I have one output or two outputs depending upon the data set we have. So now I would like to know how many packages are available for ANN. And in R, what are the packages? R packages, because we're always talking that deep learning, mostly Python is what people are preferring, but there are few packages which are suitable with R as well. So what are those packages? Any few, 2 or 3? You all know that it is NNet, right? You have one more package called neural net. Depending upon your output, you are using NNet or neural net, continuous or classification. Then you have deep net, right? You have something called as MX, Metar, right? you have a package called autoencoder. Right? So these are a few packages which will help us. They're available for more specific tasks. You have many others, but basically, I just said few packages which are related to deep learning. Right. Now, when you talk about, we were discussing the last few days about the neural network concepts, where few things are covered, like what are the gradient descent algorithms, right? What are the gradient descent algorithm, and what are neural networks, right? So how it goes when we talk about neural network, right? Definitely, whatever I have drawn here, we have the inputs. The primary function is to set the inputs, perform some complex computations, then use the output to solve the problem. So they are used for a lot of different applications. One example would be your classification. So though we have lot of classifiers, you have logistic, you have support vector machines, you have decision trees, you have random forests, right? And of course, we have neural networks. So if at all you want to predict for any person whether he is active or sick, right? What will you do? You take all the input information, right? You take height, weight, body temperature, and you need to classify, or you need to say predict whether he is an active person or he's some sick or dull, something like that, right? It can be solved using the approach. What we are talking is a neural network also. So the classifier would receive the data about the patient, process it, right, and gives a score called confidence score. So a high score would indicate that high confidence that that patient is ill, and low score would suggest that they are healthy. And the score could be the probability value of 0 to 1. So neural network is a highly structured, and it comes in layers. First layer is the input layer, last layer is the output layer, and in between you have the hidden layers, right? So this is what happens throughout our neural networks. Now when we talk about here CNN, right? When we talk about CNN, that is nothing but your convolution neural network. So what is convolution neural network? What is CNN? Convolution neural network. What are the components, or I would like to know the typical layer components, architecture of CNN. CNN nothing but convolution neural networks. So this is a typical ANN, type of ANN. So we know that it is used for mostly, we have the applications in image recognition and processing that is specifically designed it to process pixel data, right? So CNN is a class of deep neural nets, and it is applied to analyze some visual, like some image kind. So here it uses a variation of multi-layer perceptrons, and they are designed to require minimal pre-processing. So what does it do actually? It is the convolution. It is nothing but the name, the meaning or the definition, we can say that it is a process of filtering through the image to get our required, not specific pattern, right? It is a process of filtering through the image for a specific pattern, right? So if we talk about the layers associated with convolution neural network, you have conv layer, you have rectifier, linear, sorry, unit layer. So what we call it as ReLU. And finally, you have pooling layer. There is also a fully connected layer here at the end prior to your output layer in order to equip the equip net with the ability to classify your data. So a fundamental architecture, it has all the layers, CNN. So how it goes, you have input, you have conv layer, you have ReLU layer, you have again pooling, again conv layer, right? ReLU, again pool, right? Or pool is not required, again conv, again ReLU, again pool. You have fully connected layer followed by output. Right? I can write like this layer, like this. Right? This is how it goes. Right? So now if someone want to find out whether does it perform something like dimensionality reduction, is that concept is related to any of the layers or any of the parts of the CNN architecture? Dimension reduction, does this particular algorithm performs dimensionality reduction? If yes, which layer? If no, good. So you all know that layer you are using filtering. You have an activation function called ReLU. Pooling layer, right? What does it do? This pooling layer is not extracting any of the features. What is it doing? I can say reducing or downsampling the data or the image, right? So CNN can perform dimensionality reduction, and where it performs which layer means pooling layer. Right? Pooling layer does that. Okay. Now, when you talk about deep learning, we are saying, so what are the libraries, right? Like deep learning platform or deep learning libraries. How can we explain those? We all know that this library is nothing but, just now we have talked about R packages, right? We have the library. Library is nothing but, very first day you know that it is a set of functions. It is set of modules that we can call through our program. Why we want to call? Because you want to perform one task, certain task. So when we talk about deep net libraries, this is also giving us a lot of flexibility with what net selection and with what parameters. Instead of parameters, I should use the word hyperparameters. Right? So this configuration is what you can change, right? So suppose if at all we want to build any kind of neural network, right? So we code our own we use some appropriate deep net library, right? We have to get some flexibility that whatever we want to do changes, right? That should be easily available. So hyperparameter tuning should happen here, right? And the downside here is that the coding experience is what is required to use them, because whenever you are just building this particular network, you follow a procedure, right? What is a procedure? First you write what is a design, then you compile, then you fit your data to the model. These are the things. So for performing all this, what are all required, they should be available in the form of library only. For that you need to explore how do you want to do it. You want to write a custom function, you want to pull some library, or how you are going to perform this design, then do compilation, and you are fitting the model, how it goes. So you are using TensorFlow, right? Cafe, right? You can also use PyTorch, Torch, etc. Right? If you Keras definitely, which is a part. So how to use them is also a kind of coding experience you require, right? Because the way you pull different libraries, you should be able to know how we are using them also, right? You should know how you are using them. Okay, now when we talk about like the same CNN, if I say I have input image, okay, let's say I have an image, and it has to be converted into size of let's make 12 by 12. Okay, it should be 12 by 12, and a filter of size 3 by 3 with stride 1. I can make stride of 1. Now, what is the size of the matrix? What is the size of convoluted image or matrix, whatever? Yeah. Yeah. Now tell me, what is the size here? How do you calculate that? So whenever you're talking about this, right, you have a size. So I can, n is equal to 12 by 12. And my filter size is 3 by 3. Now what am I asking here? When you apply this, what should be the size of this? What is the output image size? So 12 by 12 means this is the size, friends. 1, 2, 3, 4, 5, 6. Like that I'll have 12 lines, right? Like this. The 12 by 12 image I have. For that I am applying a filter of 3 by 3. So how do I calculate? So we all know that n minus f by stride plus 1, right? N minus f by stride plus 1, right? So whatever I'm getting here, I can make it as a C. This is my convoluted image where this is my size of the input matrix. This is my size of the filter. And I should also add padding, right? If I'm saying that there is no padding, assume that you have 0 padding. No padding is done here. So what is the answer for this? You have 12 minus 3 by stride is 1 plus 1 is equal to 10 by 10 is your output. For this particular filter size of stride 1 and the input with 0 padding. Right? So we are talking about the activation functions, right? But the question comes, we have different activation functions, right? Like the big list you have, we say that ReLU, right? ReLU is used, and now you also know that there is no question of hidden layers in CNN, right? There is no concept of, we don't minute, sorry, there is no concept of hidden layers here. You call those layers as convoluted layers or convolution layers, right? Hidden layers are nothing but here convolution layers. So we know that ReLU function, right? Can we use that in output? Can I use ReLU function in output layer? No, we use this in hidden layers only, right? We use this in hidden layers only. Why? Why? What is the reason here behind that? Tell me why we can't use ReLU in hidden layers. So it's nothing but, if the output is only restricted to be a non-negative, it's a non-negative output, it would make sense that you use a ReLU activation function as output function, right? So generally, when you talk about the rectified linear activation function, right, it is called as piecewise linear function, right? That will give you the output with the input if it is positive, otherwise it would give you 0, right? We know that. Now when you use this, we are saying that it gives an output x if x is positive. It gives an output x if your x is positive, right? If x is something else, it gives you 0. So the range here is 0 to infinity. Whenever I say this brackets, right, this means that it can blow up your activation. So because of this reason, we are talking that it can't be used in the output, right? And this is not any separate component of CNN, right? So the main purpose here for applying this particular function is to increase the non-linearity in our images. Right? That's the reason that you are using ReLU in your convolution layer. That is the reason you are not using in the hidden layer, not using the output layer for normal other neural networks. Now, which function can be used, which activation function can be used as a part of output layer? And if at all we decide to predict probabilities of n classes, right, and such that the sum of all n, whatever the probabilities you get, is equal to 1. So which would help us to get like that? Well, the sigmoid function would give you the sum of the output probabilities is equal to 1. Will your ReLU function will give, or your tan H function would give, or your softmax? How can we explain this? For normal traditional algorithms also, you are using one function in the output, and that is very helpful when you have n number of classes. If I say n number of classes, you are segregating, you are having labels that you want to segregate what? Not binary. You have n can be anything, right? It could be 10 class or 4 class, or it could be anything. So softmax function is used in the output. Why? Because this softmax function would spill out the probabilities for each class. And classes are there, no? For every class, it spills out the probabilities. Because it spills out the probabilities, whichever is having the maximum probability, that would be taken as the classification. It's as simple as that. Suppose you have 1, 2, 3, 4, 1, 2, 3. This is the input, right? So if at all you're applying softmax on this, so you get probabilities, right? Now let me write few probability values, maybe. Right, some randoms. I'm just writing few. For each this thing, you get some probability values. Right? So the output has the most of its weight where, which one is maximum? I think this is the maximum. This means fourth one, 4. So this is where the function is normally used for, to highlight the largest values, right? And softmax is not scale invariant, right? So if at all you add all these probability values, what you have to get? Because that condition is always should be satisfied, right? Sum of the probabilities should be equal to 1. Right? Yeah. Next. Now, if at all we are talking about bagging and boosting, right? It's similar to, like, can you compare that? Can you compare dropout, or can dropout be compared, right, with bagging or boosting? Can we do that? If yes, how? In regular machine learning scenario, can our dropout? Now you all know that what is dropout, right? What is a dropout? It is a regularization technique, right? And mainly use it for overfitting problems. So it's very efficient way of performing what is called as model averaging, right? With neural networks. So earlier also we have seen, I think this question is asked, but with bagging or boosting, can you compare it? That is what is my question. So you are dropping off few neurons, right? You drop off. So maybe this is not connected. It's connected. Some of these neurons are connected. This is dropped. Right? So you're dropping off few. So if you do this, how it goes? How is it compared with bagging or boosting? Or no? So we can say that, it is some kind of form of bagging only, because in each model, in which that every model is being trained on a single case, and each parameter of the model is strongly done, regularization is done by sharing it with the corresponding parameter, right? So here also we have large weights when you have in your neural networks. When you have that large weights, you have like an what is a hint kind of thing for more complex network, and that complex network had overfitted your training data, right? If at all we talk about a large network with more training and the use of weights, right? The use of weight and the constraint, whatever weight constraints are there, those are suggested when you are using this dropout technique. Anyway, that is exactly correct. Dropping out few nodes in the network means some complexity is getting reduced, and it's a very good effective regularization method, right? So this is an extreme form of bagging here. Dropout is compared with bagging, right? So every model will train us on a single case, right? And every parameter of the model is very, very strongly regularized by sharing it with the corresponding parameter in all other models. Okay, now, so when you talk about overfitting, right? Are we the first thing just now we have discussed, when there is a possibility, overfitting also can occur in neural networks. So how do you handle? One method, what I told is dropout method, right? So this method will approximate your training a large number of neural network with different architectures in parallel. So this particular dropout, it even has the effect of making, the training process or forcing the nodes within a layer to take more or less responsibility for the inputs, right? So there are few parameters also you have to think of when you talk about this. And what is the dropout rate, right? Can you use it with all the network types? Or what are the grid search parameters you pass, right? So if at all you want to use it with all the network types, it can be used with most and all types of neural network models, right? We can use this for all, whether it is what you say, multi-layer or CNN. Okay, so when you talk about dropout rate, here the default interpretation of the dropout, right, hyperparameter, it's a probability of training a given node in a layer. If at all you pass something like 1.0, it means no dropout. If at all you write 0.0, it means no outputs from the layer. A good value for a dropout in a hidden layer is what you have to choose, and that choosing is between 0.5 to 0.8. and the input layers use a large dropout rate that is nothing but 0.8. Right? When you talk about grid search parameters, instead of guessing some suitable dropout rate, right, you can test different rates systematically. You test values between 1.0 to 0.1, right? You can write of your own choice, right, with an increment of 0.1. So this will help us to just find out which would work better or the best for our specific model and for that particular data set. And also, we can also find how sensitive the model is for this dropout rate, right? And one more technique you can follow is here batch normalization, right? So batch normalization is a technique for improving the performance as well as the stability of the neural network. So what is our main idea behind this normalization, batch normalization? That it is to normalize the inputs of each layer in such a way that they have a mean output activation of 0 and standard deviation of 1, right? So how you can use that? You have a function here, right? You have to pull from keras dot layers. From that you go for, from layers you have normalization, right? You would import batch normalization, right? You would import batch normalization. So you just write like this, right? You write model dot you want to add. Whether you start that you want a sequential model, then you will add your dense network. What are the inputs you have? Let me write it properly here. So from keras dot layers dot normalization, import batch normalization, right? So you know the process. How do you write model dot sequential, right? Then you will add your dense network, right? With your what are the inputs you have, input dimensions, etc. Then you can add batch normalization. Then you can add your activation function. You can also add your dropout function itself. I think it should be capital D. Dropout. What is the rate? Right? This is how you write your design first. Right? So this is a input layer. Again, you can write set of things for your hidden layer. Then you can write set of things for your output layer. And then you do compile. Then you fit your model, train your model. Right? In hidden layer also you can make it, you will add your dense, you will add your batch normalization, you can add your activation function, you can add your dropout rate. Right? The only difference you have here, your activation function would be tan or ReLU something, but your activation function would be your softmax. Right? This is how your you do reduce this, what you call it as overfitting problem. Right? Now we are talking about anyway pooling, right? Pooling exists in the convolution neural network. We all know that. But what does it do actually? Main thing here, when it is added to your CNN, right? What is that you have here? You have something called as translation invariance. So the translation invariance is induced when you use pooling. So that is one of the advantage when you use max pooling. Okay, let me put the question. I forgot to write it. Okay, yeah. We can make it as purpose of pooling layer. Right? So when you're adding it to this thing, an advantage is that translation invariance. It provides a form of translation invariance. Invariance means tilted. Yeah, you have a face now. Nowadays we are taking selfies, right? You know which angle selfie would work more. Whether it is total images like this. Assume that this is an image. So no, you're not now. No one is taking nowadays selfie. They put a yo like this and they have head tilted like that. That would not, that it would even capture the such kind of images also. So it would recognize an object as an object, even it appearance varies in some way. Just imagine that it's tilted like a selfie. So it would it preserves the object's identity category, right, across the changes in the input, visual input, right. It means that invariance means tilted. Just in normal understanding, it is tilted also. You have this particular layer would recognize the object. So the translation has a specific meaning, right? It has a specific meaning. So you remember in a geometry, right? It's nothing like a type of conversion or something like that, right? It is nothing but each pixel or pixel values in the image, it has been moved to some amount, some tilting in same direction, right? So it could be tilted this side, it could be tilted this side, right? Upside, downside, anything. So you can call it as CNN, and using your max pooling, right? It's equal to your translation invariance. Right? This is my total image. So next image could be anything. It could tilt it also, it would work. Right? So whenever you're talking about all this, right? So what to, I can say that whenever you want to, what is that, classify, right? Whenever you want to classify an image, which activation function cannot be used here? Which one would not help us? Just now I have discussed this. ReLU, right? Now tell me the difference between ReLU and leaky ReLU. Rectifier, linear unit. Leaky, rectifier, linear unit. Now what is the difference here between both of them? So a unit employing a rectifier, so how do you draw that? You can just make it into a two-dimensional space like this. And this is your y or x. Now Let me change color. Yeah, this is what you have in your ReLU. This is a ReLU function. So this is my f of y. So f of y is equal to y here. F of y is equal to 0 here. And this is my f of y. This is how what is your ReLU. It means that the range is from 0. You don't know what could be the y. It could be anything, right? Infinity. That's what I just now showed. So you're writing this bracket. It means that it includes 0 and you don't know what would be the value, the normal basis. Now, what happens in case of leaky ReLU? How is that figure going to be? I take the same. You have your y. Then I have to draw the range, right? So this side anyway it is the same, friends. Here it is the same. But what happens this side is a little bit of, right? Some value you can take. This is your f of y, right? Here anyway f of y is equal to y, but here f of y is equal to some value here. We can make it as ay. Here f of y is ay and it is not 0, right? In case of leaky ReLU. The leak helps to increase the range of ReLU function. So usually the value of a here is equal to 0.01. Okay. Then if your a is not equal to, right, if your a is not equal to this number, right, if a is not equal to this number, it is called as randomized ReLU, right? So what is the range here for this leaky ReLU? Minus infinity to infinity, right? It is minus infinity to infinity. So this allows a small positive gradient when this particular unit is not active, right? If it is not active, there is a difference between your ReLU function and leaky ReLU. Okay. 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 Now, yeah. See. Consider a normal, simple multi-layer perceptron. Okay. So, okay. Consider MLP. Okay. In this model, I want this particular model has three, my bad, 1 minute. Yeah. It has 3 neurons and you have inputs 2, 3, 4. Okay. Assume that I am giving you weights, okay, to the input neurons, and the weights are maybe, yeah, we'll take a count like this: 4, 5, 6. Okay, so let me make it as respectively. And finally, what is that you have to do is activation function, right? Assume your activation function is linear constant of value 3. What is the output? what should be the output here? You have 3 neurons, right? What should be output for this? So you know that 2 into 4 plus 3 into 5 plus 4 into 6. Correct? I'm going to write 2, 4, 3, 5, 4 and 6. Right? 3 neurons are there. So you add up, right? 8 plus 15 plus 24. This is 23 plus 24. Should be 47. 141. This is the output. Right? So you should calculate the output is what is my question. What's the output here? Okay. Now, so usually we are talking about what okay, yeah, this convolution layer, right? Can it perform various types of pre-processing, friends? Can convolution layer perform various types of data pre-processing? Various types of data pre-processing. Like rotations in the input, scaling, can perform any transformations here? Yeah. CNN cannot do that, friends. CNN can't do that. Data pre-processing steps means you need to do scaling, you need to do some rotations, right? These are to be done before you pass your model, right? So whatever you are talking about the scaling and the rotations, those are provided as input to the neural network. And we have to do that pre-processing before you pass as an input to it. That's the reason we are saying that it can't do these things on its own, right? It can't do these things on its own. So if your what you call, yeah, what happens if your learning rates, right? What happens if the learning rate is very large and very low? What happens to that? What would happen if the learning rate is very, very high and very, very low? So, yeah. So when your learning rate is too low, right? Training of the model would progress very, very slowly. As what happens, minimal updates of to the weights is going to happen. So it will take many updates before it is reaching the minimum point. So what is that you have here? If at all you are trying to draw this, right? You have your theta here and you have your g of theta. So we want minimum, right? Our aim is minimum loss. So the decrease here, what you are trying to check here. So when it becomes too low, this is what is going to happen. Means it would take so many updates. It will take many updates before it would reach your local minima. Right? Now what happens if it is too high? If it is set to too high, because it's your parameter what you are passing. It's a parameter what you are passing. So if you are setting that to too high, it becomes very, very undesirable, friends. It becomes undesirable. Like it behaves, a divergent behavior is what we see to the loss function, because due to drastic updates in the weights, how that looks, how the weights gets updated, if you take the same graph, maybe the weight started here, it would touch here, again it would touch here. This is going to happen if your learning rate is too high, right? If it is too low, if this is too high, this is how your weights get updated. And so what it means that drastic updates in the weights change, and it may also fail to converge. Sometimes, yes, model may give you good output also, or even diverge also, right? So this is what happens here whenever you are trying to change your learning rate. Right? And why we are using TensorFlow, friends, here? Why do we use TensorFlow, most preferred library here? The only reason here TensorFlow became very, very famous here is that it provides you C++ and Python APIs. It has faster compilation time when compared to your Keras and Torch, right? So this TensorFlow supports both CPU and GPU computing devices, right? Now, what do you mean by tensor in TensorFlow? What happens? What is this tensor in TensorFlow? So we know that TensorFlow is what? It's a library. What is a tensor meaning in a TensorFlow? It's nothing but a mathematical object, right? You are representing in a form of an array, but with a very, very high dimension. So these are nothing but the array of data, we can say, with different dimensions, different where you are passing that particular different dimensional data to your neural network called tensors. So if I say tensor of maybe 5 by 4 dimension, so how would I get that? 1, 2, 3, 4, 5. This side 1, 2, 3, 4. This is not there. Right? This is passed to your input layer, right? Then followed by your hidden layers and rest of the story, hidden layers and output layer. Okay, friends? So we'll stop here. Thank you all. We'll connect next week, same time. Thank you.